welcome back. This is going to be a video for calculus. Um, there are really two topics left that are, one of them is in every standard Calculus 1 class. One of them's not, but it is standard in an AP Calculus class. So the first topic we're going to talk about today is the concept of what is a slope field. And that is the one that, if you take Calc 1 at a university, this might not be in there, but it is on the AP syllabus, and so we're gonna do it. This is kind of a relatively new topic. It's interesting. I took an AP. I was at an AP Summer Institute about 15 years ago, and the professor there, he'd been a math professor his whole life, said he had never heard of slope fields, until he started being involved with the advanced placement program. So I'm not going to say that it's an obscure topic, but it's certainly not standard across all Calc 1 courses. But it is in advanced placement. So what is a slope field? Well, let me just briefly tell you what a slope field is. A slope field is a graphical representation of a general solution to a differential equation. In a recent video, we talked about what a differential equation was and what a general solution to a differential equation is, as well as what is a particular solution to a differential equation. We learned how to algebraically come up with a general solution to a differential equation and a particular solution. Like I said, what a slope field is it's a graphical representation of the general solution to a differential equation. And once you have that graphical solution to the general solution to a differential equation, you can use it to find a graphical representation of a particular solution to a differential equation. So what I'm going to do, I'm going to put just a simple differential equation up here. Dy by dx equals x over y. Okay, so that's a differential equation. It's a differential equation because it's an equation that contains at least one derivative, and the derivative is right there, dy by dx. Now, I could solve that algebraically. If you notice, that's a separable differential equation. I can move the y over here, move the dx over here, integrate both sides with respect to y on one side, x on the other side. Solve for y, get a general solution. Okay, that's not what we're going to do here. What we're going to do is we're going to use this differential equation to create a slope field. And that slope field will be a graphical representation rather than an algebraic representation of the general solution to this differential equation. Okay, so what we do is we start by making an xy coordinate plane. Okay. Now, I'm not going to make a very big slope field right here. I don't really have room. In general, if you're, that AP practice exam that I sent you last week had a slope field problem on it. And if you look back at that, if you want to pause the video, take a second to look back at that, it had a graph already put on the test for you with some points on this graph. So I'm just going to go 1 unit. Well, I might go 2 units in one direction. Let's do this. So I'm going to put a point at every spot on the graph whose coordinates are integers. Okay, so like for instance, that first point that I put up there, its coordinates are -1, +2. So its x and y coordinates are both integers. I'm going to put a point everywhere where that's the case. Okay, so like this will get a point. Here's the point 1, 1. Here's the point 2, 2, 2, 1, etc. And I've already made probably a bigger slope field than we're going to have time to create. But if I get you started, it's not very hard to create a slope field. Okay, so remember, on this graph, we're going to put a graphical representation of the solution, the general solution to this differential equation. Now, let's think for a minute about what this equation means. this says that the derivative of y with respect to x can be found by taking the x coordinate of a point divided by the y coordinate of the same point. Okay, so another way to say that is the rate of change of y with respect to x can be found, is always found by taking an x coordinate divided by a y coordinate. So for instance, if I wanted to find the rate of change of y with respect to x at the point 1, 1, well, at the point 1, 1, x is 1 and y is 1. 1 over 1 gives me a value of dy by dx, a value of the derivative of just 1. Okay, so the rate of change of the solution curve, the solution to the differential equation would be 1, right there at 1, 1. So what I do to create this slope field is I'm going to make not just an xy chart, but I'm going to make an xy chart that has a column for x values and a column for y values, but also a third column for the values of dy by dx, in other words, the value of the derivative of y with respect to x. So I'm going to make it right here. Okay, so I've got a column for x, a column for y, and a column for dy by dx. Now, so what I'm going to do is I'm going to just go down the chart and I'm going to put some points, okay, the coordinates of some points that I have on this slope field that I'm getting ready to create. I'm going to put those, the x and y coordinates of some of those points in this chart. Now, what I'd want to do if I was going to create the slope field for all of the points on here is I'd have to have, 1, 2, 3, 4, by 1, 2, 3, 4. I'd end up with 16 different sets of coordinates there. I'm probably not going to have room to do that. But we'll try to do, 4, 5, 6, 7 or so. Let's start with the point -1, +2. Okay, so that's the point, the upper leftmost point on the slope field, the graph on which I'm going to create the slope field. So I put in the x and y coordinate of this point. And then what I'm going to do is I'm going to use that x and y coordinate to find the value of dy by dx at that point. And so since x is -1 and y is 2, this would be -1 over 2 would give me the value of dy by dx for that point. So under the dy by dx column, I'm going to write -1 over 2. Okay, now, I tell you what, let's go ahead and see what the graphical consequence of that is going to be. That means that the slope of any solution curve at this point is going to have a slope of -1/2. So what I'm going to do is I'm going to put a little tick mark. Okay, it's going to be a segment, kind of a short segment, that's going to pass through that point that's going to have a slope of -1/2. Okay, so -1/2, that means for every 2 units I go to the right, I'm going to go down 1 unit. So I just have to estimate it, and it might look something like that. Okay, so I hope you can see that. Teddy, will you make sure that you can see this little segment that I drew here on the screen?
Yeah.
Okay. So I've made one little slope segment on my slope field. Okay. Let's do a second point here. Maybe I'll do -1, 1. So that's the point right below this first one. So -1 over 1. So my x coordinate's -1, my y coordinate's +1. So -1 divided by 1 would be -1. And when I make the slope segment through this point, it'll be a little bit steeper in the negative direction than that first one. And maybe like this, for every 1 unit I go over, I go down 1 unit. Now, let's look at maybe a couple of, I think that just looking at those 2 points, you're probably going to figure out how to do most of the rest of the slope field. Every one of these points is going to have a slope segment that passes through it, and the slope of that slope segment is going to be found by, using the x and y coordinate of that point. Let's talk about what it looks like, maybe let's do this next point, the one right below here. So the point right here is what I'm talking about. The coordinates are -1 and 0. Okay, well, -1 divided by 0, that's an undefined expression. Division by 0 is, and we know that if a slope is undefined, it's a vertical line that has a slope that's undefined. So what I'll do for this one is I'll write undefined I'll just write UND. And then my slope segment there will go straight up and down, okay? And, then I can come over here and at 0, 0, 0 over 0, that's indeterminate. So I'm not going to be able to put a slope segment at all there at 0 over 0, or sorry, at 0, 0, because I'll get 0 over 0. So I'm going to completely ignore that point on the graph. I can come maybe right here. I'm at the point 0, 1. Okay, so now I get x is 0, y is 1, so my value of dy by dx is 0, and my slope segment will go straight across like this. Okay. Now, once I have the slope field complete, okay, one task that they often ask you to do on the AP exam is to create a slope field. And it really is just as simple as this. You have to be given a differential equation. You have to make a 3-column chart. Okay? For every point that they give you on the grid, which they would give you a grid, you put the coordinates of that point in the columns, and then you use those, you substitute them into the equation, the right-hand side of the equation for dy by dx. Sorry, Teddy?
I have to go to my Google Meet. Someone else has
What
to
time?
take control. It's at 11.
Oh, you're fine. I'll wrap this up pretty soon, okay? All right, so anyway, one task is to create a slope field, and that's how to do it. This would have this is a pretty big slope field, but it doesn't take that much time to do. You just kind of go one point at a time. Now, once you have a slope field created, okay, and I might put a couple more points on here, like 1, 1 would be a 1, 1, 2 would be a 1/2. 0 or 1, 0, that's going to be undefined. 2, 1, that would be steeper. That would be 2 like that. Okay, I'm not doing that completely right. And then 2, 2 would be another slope of 1. Okay, now once I have a slope field created, the other thing that the AP exam often asks you to do is to draw a particular solution for the differential equation based on the slope field that's been created. Okay, to draw a particular, remember, to find a particular solution to a differential equation algebraically, we need a set of initial conditions. We need a point through which the solution curve passes. Okay, same thing here. I need to know one point that that's on the particular solution curve. So let's say I wanted to find a graphical representation of the particular solution to this differential equation for the case where it passes through the point 0, 1. Okay. All I do, and I'll get a separate color here, is I put my pencil on that point, because I know my solution curve has to pass through that point. And then I simply follow the contours of the slope field to create the curve. So I know that as I come out to the right here, the slope segments start to tilt in the positive direction. So I'm going to start to kind of tilt that way a little bit, and I might end up going like that this way. And it looks like the same thing kind of happens here. I get bumped up this way and so on. Okay, and that's how you do it. It's that simple. Slope fields are a very simple concept. What you have to understand is, number one, a slope field in general is a graphical representation of the general solution. If you remember, the general solution to a differential equation algebraically represents a family of functions, all of which satisfy that differential equation. They're all solutions to that differential equation that all differ just by a constant. Okay, that slope field represents that same concept graphically. A particular solution to a differential equation algebraically is a single function of y equals a function of x. Okay, it's a single curve. Okay, a single function, and the graphical representation of a particular solution. Using a slope field, you go to whatever point you know that the curve has to pass through, and you put your pencil there, and then you follow the slope segments to complete the curve. Okay. Listen, I know I said we were going to do 2 topics, but apparently my cameraman has prior obligations, so I'm going to come back here in a little bit. I'm going to try to find a substitute, a pinch cameraman, I suppose, and we'll talk about the second topic that I promised you today. Okay, so thanks for watching. See you in a few minutes.